So this is our first titration experiment, experiment 5L, determination of citric acid in soda. The idea here is that we are going to mix an acid and a base and measure how much of the base is added, and that will allow us to determine how much acid we had in our sample. So in the burette, we're going to have sodium hydroxide, and in the Erlenmeyer flask, we're going to have our acid sample. So one of the problems with sodium hydroxide is that the molarity will change somewhat over time, and so we have to determine the molarity of the sodium hydroxide solution every day when we are going to use it. In the first part of the experiment, we're doing what's called a standardization. This is to measure the concentration of the sodium hydroxide. We know that it is approximately 0.1 molar, but we want to know it more precisely. So what we're going to do is we're going to put our sodium hydroxide in the burette, and we're going to put an acid that we know the amount of in the Erlenmeyer flask. And that acid is going to be oxalic acid dihydrate. This is the formula right here. We're going to be using its molar mass, and so when you calculate the molar mass, be sure to include the 2H2O. So we're going to measure a certain mass of the oxalic acid dihydrate. We're going to titrate that solution with sodium hydroxide until the reaction is complete, which we'll recognize by the color change. And then we can measure the volume of sodium hydroxide that has been added. Our goal here is to find the molarity of the sodium hydroxide solution. Remember that molarity equals moles divided by liters. So here it's moles of sodium hydroxide divided by liters of solution. The liters of solution is measured right here. Well, it's measured in milliliters, but we can fix that. So we'll take our milliliters of solution, sodium hydroxide solution, and we'll convert that to liters of sodium hydroxide. And this number will go in the denominator here. To find the moles of sodium hydroxide, we'll start with the grams of oxalic acid. So grams of H2C2O4.2H2O. We're going to convert that to moles using the molar mass. And then we can convert that to moles of sodium hydroxide using the mole ratio from the balanced chemical equation. So here we see there's no coefficient for the oxalic acid, so that's a 1, and there's a 2 in front of the sodium hydroxide. So we're going to use 2 moles of sodium hydroxide for every 1 mole of oxalic acid. So we calculate the moles of sodium hydroxide used and the liters of sodium hydroxide used, and then we take the moles and divide by the liters, and that will give us the concentration, the molarity of the sodium hydroxide. We can sort of check our work because we know that it's approximately 0.1 molar. So if we end up with something like 10 or 0.0005, that indicates that we did something wrong in our calculations. It should be pretty close to 0.1. After we've established that, then we can go on to the second part, which is the determination. Let's just get rid of this. In the determination, we're going to use the sodium hydroxide that we just standardized to find the concentration of an acid. In this case, it will be in a fictional soda called 6-down. Citric acid in this soda. So here what we'll do is we'll use the concentration of the sodium hydroxide that we just determined. And we're going to use this reaction here. This is citric acid. Citric acid reacts with 3 moles of sodium hydroxide to form sodium citrate and water. So here we have another stoichiometry calculation. So we're going to measure a particular volume of the soda. It's going to be 10.00 milliliters. And then we have our molarity from the first part, moles per liter. It's approximately 0.1, but we've determined it more precisely than that. And then we're going to measure how much sodium hydroxide was used to titrate that amount of citric acid. So again, we're calculating a molarity. Molarity for the citric acid will be moles of citric acid divided by liters of the acid solution. In this case, it's the soda. So let's just write soda here. Liters of soda. Well, we had 10 milliliters of the soda. So we need to convert that to liters of soda. And then this number becomes the denominator in our molarity calculation. We're going to use the volume of sodium hydroxide and the molarity of the sodium hydroxide to calculate the moles of citric acid. So we've got milliliters of sodium hydroxide. We'll convert that to not moles, to liters. Liters of sodium hydroxide. And then to moles of sodium hydroxide. And the conversion factor here from liters to moles is the molarity that we calculated in the standardization part. Once we've found the moles of sodium hydroxide, we can use that to find the moles of citric acid. The conversion factor needed for that comes from a balanced chemical equation. 1 mole of citric acid for every 3 moles of sodium hydroxide. Then this value, the moles of citric acid, will go in the numerator here. We're dividing by the total volume of soda that we titrated, which is this value up here, and that will give us the molarity of citric acid in the soda solution. To standardize the sodium hydroxide, it's important to get a precise mass of oxalic acid dihydrate. And so there are a couple of different weighing techniques, but I'm going to use the one that is listed in the procedure. Here you tear a piece of weighing paper. That means you put the weighing paper on the balance and you press the tear button so the balance reads 0. So now the paper is considered part of the balance. And then you add between 0.1 and 0.125 grams of oxalic acid. Doesn't matter what it is as long as it's between those two. You're going to record the precise mass, that is all the digits. We want all the digits that are displayed on the balance. Then we're going to take the oxalic acid on the paper and we're going to add it to a clean Erlenmeyer flask. It's fine that it's wet, it just needs to be clean. And then we're going to put the paper right back on the balance and record the mass of the paper again. Now, if all of the oxalic acid got into the flask, then the mass of the paper will show as 0. If some of the oxalic acid dihydrate stuck to the paper, then the mass will not be 0. And that's what we're looking for, because sometimes these acids are a little bit sticky and we don't always get all of it into the flask. So when we're determining masses by difference, it can be helpful to look at the words. So we've got, we're weighing the paper plus the oxalic acid, dihydrate. And then afterwards, we're weighing just the paper. And so let's pretend that this was 0.1111 grams. And afterwards, the paper was 0.0001 grams. Sometimes it's confusing looking at the numbers. What do we subtract? Looking at the words can help. So here we have paper plus oxalic acid and just the paper. If I subtract the word paper from that sentence, then I get oxalic acid dihydrate. If I subtract these two masses, I get the mass of the oxalic acid dihydrate that was added to the flask. When we're doing titrations, we're going to be reading the burette multiple times before and after each titration, and so it's very important to understand how to read the burette correctly. So this is a zoomed in picture of an initial reading for a titration. If we look at the numbers here, we see that this is a 6, and here's 7, and here's 8. And so it's very important to understand that this 6 does not mean that the burette has 6 milliliters in it. The 8 does not mean that it has 8 milliliters if the level is down there. Think of this as a ruler. So it's just kind of a ruler that we're using to measure. So 0, 1, 2, 3, etc. We are not measuring, we're not measuring the volume in the burette. That's not possible and it's not meaningful. We are going to measure how much sodium hydroxide was released from the burette. And we'll do that by recording a starting place. Say we started here and we ended up here. The difference is the volume that was added. So when we read a burette, we just use the numbers as if they were a ruler. So we're looking at the bottom of the meniscus, the curved part here. And because of the colors behind it, we can see there's it's dark because it's reflecting some things around it, so that's convenient. Here we have a line that represents 7. Here's a line that represents 6. And then we need to look at how many divisions are there in between. Well, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 10 divisions. So each line represents 0.1 milliliter. We always estimate one digit. So we're going to read this to plus or minus 0.01 milliliters. Because where the lines are, there's no uncertainty. And we're going to read between the lines to get an estimate. So if we look at this, we see that it's between the 7 and the 6. That means it's 6 point something. So 6 point, and the pointer's not very small here. I'm going at the center of the dot. So there's 1, 2, 3, 4, 5, 6, 7. So the meniscus is between the 7 and the 8. So this is 6.7 something. And then we're going to estimate between the lines. Some people can do this to plus or minus 0.01. Some people just go to plus or minus 0.05. The important thing is that you have 2 decimal places. Now it's clearly not on the 7 and it's not on the 8. It's in between. And as I'm looking at that, I'm thinking it looks about halfway, so I'm going to call that 6.75. We do typically use milliliter as a unit on the reading, so I'm going to call that 6.75 milliliters. That's the reading initially on the burette. After we finish the titration, we'll look at the final reading, and then to find the volume added, we'll take the final reading and subtract the initial reading, and that will give us the volume added. And that's what we're interested in. So on the report sheet for trial 1, using our made-up numbers there, I would say that the mass of the oxalic acid and the paper was 0.1111 grams, and the mass of the paper after I put the oxalic acid into the flask was 0.0001 grams. I had my initial burette reading of 6.75 milliliters. I'm going to make up a final reading. Let's say this is 26.75 milliliters. So you're going to repeat the titration 4 times to get 4 trials. Then we take our soda and we're going to pipette 10 milliliters of soda into a flask. And that's going to be the same for all of them. And you'll see in the video that I used the same pipette and I measured 10 milliliters of soda into each of the 4 flasks. And then we'll record the initial burette reading and the final burette reading for each of the 4 titrations. In the calculation section of your report, this is asking us to show one example of each calculation, including the units. Sometimes students misunderstand what this means. I want to see the actual calculation. So we've already done this first one, mass of oxalic acid. The way we calculated that is we took the mass of the oxalic acid dihydrate on the paper and we subtracted the mass of the paper and we got 0.1110 grams. It may seem a little silly. Why is she making us write that out? That's so simple. But it's important because we need to be able to show others what we subtracted to get our numbers. Because sometimes we do it correctly and sometimes we do it incorrectly. The next calculation is finding the moles of sodium hydroxide using this path. And I'm going to be a tyrant here and say you have to do it this way. Use dimensional analysis, grams of the acid dihydrate to moles of the acid to moles of sodium hydroxide. Show that calculation here. The net volume of sodium hydroxide in liters. So in my example, we had 26.75 milliliters. That was the final reading. And we'll subtract the initial reading, which was 6.75 milliliters. I made up these numbers to make it a little easy on myself. So when I subtract those, the volume is 20.00 milliliters. I want to keep the correct number of significant figures. Both of those numbers had 2 decimal places. My answer should have 2 decimal places. And now I'm actually going to show how I convert this using metric prefixes. I have 1 milliliter and milli stands for times 10 to the minus 3. And so this is going to be 0.02000 liters. The next calculation is the molarity. Here I'm going to take the moles of sodium hydroxide and divide by the liters of sodium hydroxide solution. So the answer to this part is the moles of sodium hydroxide. Here is your volume of sodium hydroxide solution. And so whatever we got from up here will go here. Do the math, report the molarity with the correct number of significant figures. There should be 4 significant figures and it should be close to 0.1 molar. We've done Grubs Test before and we're going to do Grubs Test again here. You can't do the Grubs Test until after you've done all 4 calculations. Again, the Grubs Test was explained in Experiment 1. So obviously in this online class, you are not actually doing the experiment, you're watching me do the experiment. There are advantages to that as well as disadvantages. But to get the most out of this experience, I want you to pay attention to these setup steps. Large beaker, especially here. So in the video, I demonstrate rinsing the burette with DI water, rinsing it, conditioning it with sodium hydroxide, and filling it. and getting the air bubble out of the tip. So as you watch that video, make note of the steps that I'm going through here, so that in the future, when you need to do this in person, you'll have an idea of what is being done. Then I'm also following these steps here: tear the piece of paper, weighing paper, measuring out the oxalic acid, recording the precise mass. That's part that you have to do. Adding the acid to the flask, reweighing the paper, and then you need to record the mass again. So in the results and discussion part, after you've filled all of that in, for the discussion, what I'm asking to do is answer this question. So in that standardization part, the first part of the experiment, how would the calculated sodium hydroxide concentration be affected if some of the acid solution got splashed onto the flask walls and it was not rinsed down before getting to the end point? And what I mean by that is, would the concentration be higher than the actual concentration, the calculated concentration? Would it be lower than the actual concentration? Or would this not have any effect? And so, how do we think about questions like this? Well, we start by drawing a very ugly Erlenmeyer flask. Okay, we have solution in here. And this is our acid solution. And here's our sodium hydroxide coming down, being added. The question here is, what if we have some droplets of acid that got stuck on the side? As my sodium hydroxide is coming in and reacting with the acid, is it going to react with the acid that's stuck up here? You need to figure the answer out to that. And if it does not, how is that going to affect the amount of sodium hydroxide needed to react and turn the solution pink? And then how is that going to change the calculated molarity? Obviously, any errors that we make in our experiment do not affect the actual concentration. It is what it is. But mistakes that we make can affect the calculated concentration. And it's important to learn how to think about these possible errors so that if we have a result that does not come out as we expected or comes out to be definitely wrong compared to a known standard, we need to be able to think about what could possibly have gone wrong. And so we need to be able to answer questions like this, where we identify, well, this is a possible error. Would it make my calculation high or low?